Hello, everybody. Can you hear me? So, very happy to welcome you back on the superposition stage from my side. My name is Lukas Klingholz. I'm working at Bitkom. I'm head of cloud and AI, and I'm very happy to moderate the afternoon sessions on the superposition stage today. As before, if we have time, we will take questions after the presentation, so feel free to ask whatever question you want. A colleague will bring a microphone then, so we can make it as interactive as possible. I have the honor to introduce the next speaker, the first speaker in the afternoon session on this stage, who is Enrique Solano. He's Chief Visionary Officer at Kipu Quantum, and he's talking about bridging the quantum frontier, exploring quantum computing paradigms for industry advancement. So the stage is yours.
Thanks. To change the slides. Okay, thanks. Okay, so thanks a lot for the introduction and for the invitation to join this Quantum Summit event organized by Bitkom. I appreciate that you joined this early session in siesta times. And yeah, so I will try to wake you up. So essentially, in this, it's a 20-minute talk, but I will try to make it 15, 17, and I hope you can ask some questions. You can also, during my talk, just raise a hand and don't throw tomatoes, but make polite questions, and I'll just try to answer them. So Kipu Quantum is a startup company in quantum computing that was created a couple of years ago when I was living in Munich. Since 1 year, since we got our first funding round, we moved to Berlin, the capital of Germany and the capital of Europe and the planet and the Milky Way, right? The solar system. Why?
Because it's scratchy.
So you can put it like that, or it's better like that. Each time somebody gives me a microphone, I think I have to sing, and I feel me now stressed, you know. So essentially, I was saying that Kipu was created 2 years ago, but since 1 year, the technology team is based in Berlin. We have also our management offices in Karlsruhe. Why Berlin? Because that was always my favorite city, family-wise, and also because of my personal taste. And we are rocking and trying to become leaders of quantum computing worldwide. There is no other way to create a startup than to develop a technology that will lead, and that's what we are trying to do, as I will explain you now. The main motivation of creating Kipu is because I became the most hated person worldwide because I was a strong critic of quantum computing community, as probably most of you know. And in all the continents, because I have been traveling between North America, Europe, and Asia in the last 25 years. And then I said, okay, let us show the community how you can make quantum computers useful now. You know, so it's very hard that you hear the word future in my mouth. I don't know if you ever met it. Each time I meet future, it becomes present. So I said, let us make quantum computers useful now. And useful means for industry use cases, not only for academic goals. And I will try to show you how. So our co-founders are here. I started like CEO, and I don't regret, but I don't want to become CEO. When I see Daniel Folks working, then I say, wow, that's industry experience, McKinsey, BASF, now driving Kipu in a brilliant manner with a lot of know-how. It's not only that this requires skills, but also I don't want to have those skills. I want to focus because my job as chief visionary and leader of the tech is to turn quantum computers useful, as I will explain. Tobias has also an important track record in leading startups. My career, I don't like to introduce me much. You can just check Google Scholar or Google and you will see what I have achieved in the last 25 years. So this is a common point about Moore's law ending. It is not a joke. Essentially, Many people claim, no, the digital world exists, but when I check my last Mac, you see that you have neuromorphic chips, you have parallel computing, you have digital computing. So we are all already living in times of kind of cross-tech devices, and we have to move to the quantum, not only because it is necessary, because we are human beings and we need to create things that do not exist. That's the essence of arts and the essence of science and technology, right? So wherever nobody calls us, we have to go there, like we did with the moon, and we will do with the solar system. So the why, there are many reasons. Some people can claim computational complexity, which is a fundamental reason. Recently, there is also interesting moves about energy consumption that can be also strongly reduced, so you will have also energy advantage. And also the fact that it's a weirdness of the quantum aspects, that each qubit you add, there is a kind of exponential growth in the, at least in the Hilbert space dimensions and the encoding of the problems, as I will explain later. The ugly truth beyond the hype is what I was saying at the beginning. I have had the luck to collaborate and to influence most of the quantum computing efforts in the academic world and also in the industry. Many years ago, I developed many Nature papers with the Google team led by John Martinez. I worked with many people of IBM. Many of my PhD students are there. I left a strong track also in China and in Europe, in Spain and Germany. But I was a strong critic of this hype and overhype. Hype is part of life, right? That's the essence of Darwinian evolution, at least to show that we are stronger than we are, to pretend a little bit. But hype has a limit when we are able to propose science, technology, product, and business with an object that does not exist, as is the case of a logical qubit of fault tolerant. So if the unit does not exist, that's in the category of mathematical physics, that in some years may become science and physics, in decades will become technology, in decades may become product, and perhaps next century, business. And then when I abandoned my academic career to join this trend of industry and quantum computing, I said there has to be consolidated science, consolidated technology, turn it into product and make it useful now. If I were not convinced of that, I would not be here. I'm here because we have enough ideas, technology, product, and business possibilities for making quantum computers useful now. And that's the ugly truth beyond the hype. So I'm only speaking about things that are possible now in the lab and not requesting miracles to the lab to become smarter. One becomes smarter when you have ideas to make revolutionary advances in quantum computing with the existing hardware, with your encoding of industry use cases there. And not just saying, give me 1 billion qubits and I will make magic. That's not smart at all. That's weakness, chickening out from the true challenge and problem. So the way Kipu unlocks this stuff is with different technologies. I will explain in a later slide, but essentially by accepting the hardware, there is something that people have not digested very well. Quantum computers have already proved that they outperform classical computers. You can check the two claims by Google, the first one contested, the recent one with 72 qubits still open. You have the claim of Xanadu, you have the claim of USTC in Shanghai, and USTC China efforts. So the point is not whether quantum computers can do better. The problem is really to encode in such hardware, or the next generation of that hardware, industry use cases to make them useful so that somebody can come knock at your door and say, I don't know your name, but I want to pay you for that service. And that's what Kipu is about, okay? So our team is large. We are more than 30 people already, most of them 80% based in Berlin. Brilliant people, some of them my previous researchers, students, fans, haters also, that said, oh, I want to back you with my stuff. But really a team that is convinced that we can make quantum computers useful soon, and I will explain now how. So essentially, we have a lot of hidden things because Kipu is not about just making a hype and trying to sell cheap things and small algorithms for making some money, cheating a little bit the investors and then running, right? But it is really about trying to make it useful now. And we have many different technologies, but I will just comment 2 of them. One of them is the digital path, and even though we may still need 1 to 10, let's say 1 order of magnitude more in coherence time of the qubits, so that we enter into this range of 50 to 100 qubits with enough coherence time to make a circuit depth that we can enter into the regime of quantum advantage for an industry use case. That's the regime of the 72 qubits of Google, as I said. But the way we do it is by accepting hardware companies like IonQ, Quantinuum, IBM, Google, the ones that had the largest number of qubits. For obvious reasons, Kipu prefers to work with the largest hardware because we tackle that quantum advantage possibility. And the way we improve our algorithms to fit there is not just by taking existing algorithms and playing tricks of how to reduce number of gates. That's fine, that's compiling. Kipu just encodes and develops the algorithms from scratch through the general encoding in the ground state of an adiabatic quantum computer, accelerating by counter-adiabatic dynamics and turning it back into digital operations. And we have proved, we have the world record in protein folding, in portfolio optimization, in chemistry, machine learning, factorization. So in everything that is fashionable, but our technology is not developed for those verticals only, but it's a general way of encoding, a different way, a revolutionary way, I would say, because wherever we apply it, we outperform by far the previous existing record. So that's what we call the digitized counter-adiabatic quantum computing. Sounds technical, but that's the way it is. And the second revolutionary technology is something that I also invented many years ago. The digital part has only 3 years, and the digital analog I invented, I would say more than 10 years ago, and there are plenty of experiments proving its power, but it was only successful in the lab for academic cases, and now we are applying it to industry use cases. And it is based on, instead of suffering the restricted Hamiltonians and modeling of the analog blocks of analog quantum computers like Wera, Pascal, we take them as they are, I mean only mathematical constructs for no specific application, and we convert this analog multi-qubit entanglement into a step of a digital analog algorithm that composes arbitrary targeted models, and we can approach traveling salesman, combinatorial optimization, and all the applications you've heard of. If you do that, the circuit depth of a digital analog quantum algorithm is extremely short. We have cases where typical digital algorithms that take circuit depths of many hundreds can be reduced to the order of 10. That means that if you run this in Quera or Pascal with 100, 200, 500 qubits, and you just need 10 steps or 20 steps, you may be entering into a regime of quantum advantage, which I predict we are far only by days, weeks, or months, and not by decades or years. And I cannot tell you more because, of course, we are a company and we are working on that, but we have preliminary evidence that we will be showing in the next weeks and months. So as you see, our partnerships are typically very strong with the hardware companies. By now, we just use cloud-based quantum computer providers because you have to prove your technology. So literally, we challenge anyone, any competing algorithm to approach us, and we will show how we can do it 10 times, 100 times better than any competitor. And we expect that when we convince the community of the power of our technologies, we will also convince them to co-design their hardware when we will enter into a kind of systematic quantum advantage for industry use cases. But these are the technologies that we're using. Of course, we are also using Quantinuum and IonQ that are providing amazing results. Recently, this is something also kind of confidential. You see, it's so confidential that I'm sharing it here. But if you check our recent paper in portfolio optimization, where we outperform by far the results of JP Morgan, who have an amazing team of brilliant people for quantum computing. And internally, we have even 10 times better, more compressed algorithms than the ones that we advertised. And we are trying to approach now a lot of fintechs and financial interested stakeholders. So that's the way we develop our technology. I will be stopping if somebody has some questions. But essentially, when I started criticizing the community of quantum computing, those who follow me, many love me, many hate me, but I was born to say what I think and as a scientist and to do what I think works. But I was a strong critic some years ago when came the fashion of, we all develop hardware-agnostic quantum algorithms. What's that? I mean, we cannot run correctly a 2-qubit gate, and we are speaking about hardware-agnostic. So Kipu is application-specific, hardware-specific, and following hand in hand with the hardware. Our team understands hardware. There is no other way to develop quantum computing and algorithms usefully if you don't understand hardware. If you doubt that we understand hardware, you can ask IonQ, Chris Monroe, the CSO, who designed the 2-qubit gate of that company. It was myself 25 years ago during my PhD thesis in Rio de Janeiro. And I've been there, and IonQ, I've been introduced like the guy, but I don't get a single cent and a single credit. And that's why I said, let us make Kipu. Let us not only try to recover the credit we had for the pioneering work in quantum computing, but let us create this co-design spirit where you study the possibilities of the hardware that, as I said, already outperform classical computers, and use your talent and your smart ideas to encode industry use cases there, and not to be crying like babies, requesting miracles in the lab from others, and to put all the weight on our talent, on our shoulders, to make quantum computers useful now. So that's more or less where we are. This is the path of Kipu. We are now trying to close a round now, and we believe that we will be here in next months and few years to check whether what I announced is true or not. You know, to make promises for the far future is trivial. We will not be there. You know, so that's what Kipu is about. And thanks for your attention.
So thank you, Enrique. Do we have any questions? One?
Thank you very much for this very insightful talk. Could you elaborate a bit more on how you said you're basically outperforming classical computers? So could you tell us in which kind of category you already demonstrate this, and what are the metrics you measure this at?
Good point. So the statement I did is that others already demonstrated. Google has an official claim of 72 qubits using qubit sampling, outperforming. This was not contested. The one that was in 53 qubit was contested. The one of 72 was not contested. We've had Sanadu with a similar claim with around 200 modes in Gaussian boson sampling. USTC has it for superconducting circuits for qubits and also for boson sampling in photonics. So let's say the sentence that quantum computers outperforms classical computers is a trivial statement and not under discussion. You know, whoever discussed that has to prove that those can be simulated. Now, the point is not there. The point is, can we, in that hardware that has this computational power, can we encode an industry use case that is useful and somebody would pay for? That's the challenge. And the community has been split in two. The minority, which I belong, is saying, yes, let us use a smart encoding there. And the other, most of the community says, let us wait for the billion qubits next century. I am not going to be there. My challenge is now. And for answering your question, if you ask any condensed matter physicist, they will tell you that any supercomputing center blows up in the range of 60 qubits for a given spin model. That's what IBM tried to do with the 127 qubits recently with their chip, and they failed because, I mean, as I thought, I put it in LinkedIn immediately after the paper. This is, of course, not going to make it, you know, because of the circuit depth problem, not because of the number of qubits. To have many qubits is trivial, as D-Wave has 5,000. Makes nothing so interesting. So the point is, the range of quantum advantage for digital quantum computers in the NISQ era are in the range from 50 to 60 to 100 qubits. Now, the problem is the circuit depth and the encoding of the problem. It's not the number of qubits, it's the encoding of the problem in that hardware. And on the analog quantum computers, we have already, and Quera and Pascal will announce very soon, 1,000 qubits. So 1,000 entangled qubits have the computational complexity capacity of outperforming anything, nobody can simulate that since years, but it's well known. There's nothing, I'm not saying anything new. The point is, can we encode there an industry use case? And our answer is yes, but not by trying to engineer digital quantum computers there, by respecting the analog block, the analog quantum computer, and to use it as a part of a digital analog encoding that in very short number of steps, you can reach quantum advantage. So if you ask me size of matrices, You know, the record Nature paper last year of Quera 299 qubits is 2 to the 289. You know, there is not even a memory able to encode that. So the computational complexity is there, as I said. It's just missing a daring and bold mindset to encode there an industry use case. I know I'm saying for some of you some things that you are not used to hear, but somebody has to tell you the truth. You know? So there is the capacity and the potential today of making quantum computers useful. That's a fact.
Thank you.
Yeah.
Thank you for your presentation. Very insightful. I think you're just around here for more questions around the corner. Thanks a lot.